Just a little bit more on bending stress here. All right, so we covered in class, I think it was Wednesday, a little bit. The basic idea of this is that if you have a beam, and let's say we're going to bend it down, and let's say before we do that, we draw two lines on the beam that are exactly the same length, one at the neutral axis up above, and another down below, some distance of y. And then we apply a load to the beam and bend it. It's going to get into a curved shape, as you see. Now the distance straight across dx will be approximately equal to the arc length there. It may not be quite an arc. This may not be a perfectly circular curve. It probably won't be, but we could just call it that, I guess. Now, if we don't have a huge amount of deformation, those two distances are pretty much the same. So what we can do then is take that circular segment there and approximate it as a triangle. And what's going to happen then is that original length of the line below is going to change. Now, at the neutral axis, it won't, because that's the boundary between tension and compression on a beam. There's no strain or stress there. But right below it will a little bit. And we can approximate that using similar triangles. All right, so we can say the strain on that lower line is delta L over L. That's the definition of strain. Okay, now that's going to be proportional by similar triangles to delta rho over rho, which delta rho is the change in this radius of curvature. We call it rho because it's not necessarily a circle. R is generally reserved for circular radii. Rho is a more general term. So here's the radius of curvature of that beam. And we're coming off of that a little bit when we drew our second line. We're coming off a distance of y. So delta L is to L as delta rho is to rho, which is y to rho. So the strain, the normal strain in the x direction is negative y over rho, which we call 1 over rho kappa, which is the degree of curvature. So the strain in the x direction is negative kappa times y. Now we can factor up both sides by e and get to the stress. So the stress is negative e kappa y. Now, the key thing on this is that the stress is proportional to the distance from the neutral axis. So the ratio of sigma x over y is a constant. Okay? Now, if we want to draw some relationships here for stress, what we can do on this is look at what's happening with a typical beam. So I'm changing here to a simply supported beam with a load on it. What's going to happen is it's going to get a stress distribution on it. The further from the neutral axis you go, the greater these stresses are. So down below, you're going to have increasing tensile stresses for a simply supported beam that's loaded down like that. And there'll be a linear relationship there. And up above, you'll have increasing compressive stresses. So if you want to figure out what the net moment is that these stresses impart to the beam, what you can do is kind of look at how these two diagrams here would get to that. We've got on the top, we've got a compressive force pushing to the left. On the bottom, we got a tensile stress pulling to the right. The net effect of those is a couple like that. If we want to calculate the magnitude of that, we're going to take the stress times the area over which it acts. So we're going to break that beam up into a bunch of little areas. They would be more on the cross section of the beam, which is going to be kind of tough to draw here. But, you know, we have this cross section of the beam kind of like that, more or less. So we're going to take a little bit of an area there, find the stress on it, multiply the stress times the area. That would be pulling out away from the beam, kind of like that. So stress times area will get us a force, and then multiply it by how far below the neutral axis we are. That would be a moment arm, y. Okay, and add up that for each little area in that beam, and you'll come up with this couple over here, this moment. All right, now to integrate that, what we can do is a little bit of a trick here mathematically. What we can do is we can put in a term that's equal to 1, and that term will be y over y. Okay, and then we realize that sigma x over y is a constant, so we can pull that one out of the integral. So the moment is sigma x over y times the integral of y times y dA, and that's y squared dA. The integral of that is I, the moment of inertia. If you remember that from statics. So the moment then is sigma x over y times I. So m is sigma the normal stress times I, the moment of inertia of the cross-section of the beam, divided by y. All right. Now, this moment is this couple right here, but it's also the moment off the moment diagram, see? So we can get this m from the moment diagram. So what we can do then is rearrange that equation and solve it for sigma. The normal stress, you see, so what we can do if we know the value of moment off the moment diagram and the offset we're looking at from the neutral axis, and if we know I for the cross-section of the beam, we can find the normal stress at any point in that beam. It's my over I. Now, y max is called c. That's the distance from the neutral axis to the edge of the beam. So if I want to find that maximum normal stress, I take mc over I. Okay, and that's the formula we're going to work with. We'll work with this on Monday and work through an example with it. This is an important formula where you can find the stress in a beam. Another thing we can do incidentally is use this relationship we developed earlier, plug that in for the normal stress up here, and then the y's cancel, and we get a term here that relates the degree of curvature kappa in the moment. The degree of curvature, which is 1 over rho, is minus m over ei. We'll use that later. Okay, now coming back to this formula here, what we're seeing is the normal stress maximizes on the edge of the beam. And sure enough, here's a test on failing a beam. We have a jig here where we've got a hydraulic press pushing down. We've got 2 points of contact, which serves to spread the load out and get a more gradual curve so we don't get any stress concentrations. And there you see it right there. See how that lamination is pulling apart? We got tensile stress there. Once that one goes, the next one goes right there. And then it just starts propagating and working its way up through the beam, okay? So that's a tensile failure on that beam. All right, well, we'll do more of this on Monday. We'll run through an example.